Hello and good day everyone. Today we are going to present our video presentation about the ray diagram in lens. But before that, we are the group 5 and I am Jerison Carable and I want to introduce to you my group mates, Bench Garcia, Kim Janel Malibiran, Irish De Castro, and Angeline Quinto. The bending of light or sound as it passes through something like a wall or a window, as it moves from one medium to another, it can be bent, and that is what we call refraction. The ones that we are deal here are converging and diverging lens that made of glass. And so as it does, it creates an image. Sometimes the image is real and sometimes the image is virtual. For more understanding about refraction, let's watch the video.
Good day everyone, I'm Bench L.A.M. Garcia. So what is ray diagram? A ray diagram is a graphical representation of how light rays behave when they interact with the optical system, such as lenses or mirrors. It helps visualize the path followed by the light rays and can be used to determine the characteristic of the image formed by the optical system. In a ray diagram, light rays are represented by straight line with arrows indicating the direction of propagation. The incident ray represents the path of the incoming light ray, while the reflected or refracted ray represents the path of the light ray after interacting with the optical system. Ray diagrams are useful in determining the location and characteristic of image formed by mirrors and lenses. By tracing multiple rays from different points on the object, we can determine where the rays intersect or converge to form the image. It helps us understand how the image is formed, whether it is real or virtual, and characteristics such as size, orientation, and location.
Good afternoon everyone, I am Kim Janel Malibiran and I am here to talk about the definition and characteristics of converging lens. Converging lens directs light to a point at the optical center or axis of the lens. A lens that converts parallel rays of light to convergent rays and produces a real image, as long as the image is real and inverted. Light rays on either side of the lens, parallel to the principal axis, will either converge or diverge. Converging lens, parallel light rays will converge to a point. This is the focal point of the converging lens. A point that is twice the distance from the lens as the focal point is labeled 2f. To understand more about converging lens, here's a video about it.
Hello students, Ms. Watson here, and today we're going to look at how to draw ray diagrams of converging lenses. This picture here just shows the sort of diagram that we'll be drawing. So we have a couple learning goals today. You should be able to draw ray diagrams for converging lenses, and you should be able to describe images produced by converging lenses. So just like what we saw with the concave mirrors, there are a different set of rules depending on the location of the original object. So we have 5 different locations that we talk about, and we'll have different rules for several groupings of these. So one of the locations is beyond 2f prime, so that means further from the mirror than 2f prime, at 2f prime, between 2f prime and f prime, at f prime, and between f prime and the lens. So those are the 5 locations that we'll talk about. The first 3, so object beyond 2f prime, like in this picture here, at 2f prime or between f prime and 2f prime, those 3 all have the exact same rules. So we're going to group them together, and I'm just going to do one example that covers all 3. Now if you have an example in your worksheet that covers a different one, you'll still be using these exact same rules. So what we'll be doing, just like what you saw with the mirrors, it's really hard for me to draw on the tablet to get correct angles and have nice straight lines. So I'm going to be using an animation to show you what I would be drawing, and you will follow along in your notes the drawing the way that the animation shows. So our first rule is that if we have an incident light ray that's parallel to the principal axis, and we're going to draw our arrowhead on there to show that it's moving towards the lens, so parallel to the principal axis, it will refract through the focus. So it will go through F. And again, we put another arrowhead on there to show that the light is moving in that direction through F. So that's our first rule. Our second rule is that if we have a light ray that's moving through the optical center, it will continue on in the exact same direction. So it won't refract, it'll just move through in a straight line. So those are our two rules that we'll be using for these three situations. Now, since we started drawing our light rays at the top of the balloon, that means where the light rays cross, which in this picture is between F and 2F, where they cross will also be the top of the balloon, because where the light ray started is the top, so where they cross will also be the top. So we can draw our picture like this. Now, the string of the balloon went straight down to the principal axis, which means the string of the balloon of our image will go straight to the principal axis. Now, it's upside down this time, but it will go straight to the principal axis. It doesn't go straight down, it moves towards the principal axis because the original object had the string moving towards the principal axis. So this is what our final image would look like. Now, if we're describing it for the size, it's smaller. Attitude is inverted because they're facing in different directions. The location is between F and 2F, and the type is real. It's real because it's on the other side of the lens, and because lenses are transparent, light can actually move through the lens, so if it ends up on the opposite side of the lens from the original object, that is real. If it was on the same side, then that would be virtual, because light doesn't bounce off of the lens and come back like it would with a mirror, so that would be a virtual image. If it's on the opposite side, then it will be a real image. So let's take, these characteristics vary depending on which of those three locations written at the top. Depending on which of those locations your object is at, you'll have slightly different characteristics here. These are the rules that I just explained. I'm not going to read through them, but if you like, you can pause the video and write them down for your notes. So let's take a look at the example when the object is at F prime. So in this case, our first rule will be that an incident light ray traveling parallel to the principal axis will refract through F. So this is the same as the first rule that we saw last time. And again, drawing the arrowheads on there. The second rule, an incident parallel light ray traveling through the optical center will continue on in the same direction. So again, the same rule that we saw last time. What's different about this situation than the last one is that if we look at our refracted rays, they are parallel to each other, which means they will never cross. Now, we know where the top of the balloon will be based on where they cross, but if they never cross, that means there will never be an image. So if we look at the characteristics are that there is no image, so we can't describe it. Anytime the original object is located at F prime, there will never be an image. So this is always the case when it's at F prime. And here again are these are the descriptions of our light rays. I'm not going to read through them, but pause the video if you'd like to copy them into your notes. And then finally, let's see what happens when the object is between F prime and the lens. So our first light ray will be parallel to the principal axis, and it will refract through F. Our second will move through the optical center and continue on in a straight line. So again, the same two rules that we saw last time. The difference here is that if we look at our refracted rays, they're actually traveling away from each other. If they're traveling away from each other, they won't cross on that side of the lens. However, if we backtrack those refracted rays to the original first side of the lens, we'll see that they do cross. So if they're traveling away from each other, we need to back up those rays. So this is how it would look. The orange one traveling backwards to the original side of the lens, and same with the red line there. And now we can see that those two will cross on the other side of the lens, and where they cross, that's the tip of the balloon. So we'll draw the balloon. Again, with our original object, the string went straight down to the principal axis. So in our image, the string will go straight down to the principal axis, and we'll have an image that looks like this, on the same side of the lens as the original object. So if we're describing this, it's larger, it is upright because they're both facing the same direction, it's beyond 2F prime, and its type is virtual because it's on the same side of the lens as the original object. And here are those rules if you'd like to copy them down in your notebook.
Good afternoon everyone, I'm Iris Jane De Castro and this is definition and characteristic of converging lens. Definition: a lens placed in a path of a beam of parallel rays can be called diverging lens when it causes the ray diverge after reflection. Also known as divergent lens, negative lens, concave lens, or dispersive lens. A lens that causes parallel light rays to spread out, hence diverging away from the optical axis of exciting the lens.
Hello students, Miss Watson here, and today we're going to take a look at ray diagrams of diverging lenses. This picture here just shows the type of image that we'll be drawing. Now if you haven't yet watched the video on ray diagrams of converging lenses, please watch that one first, as the most difficult situation that we encountered with the converging lenses is very similar to what we'll see with the diverging lenses. So we have a couple of learning goals here today. You should be able to draw ray diagrams for diverging lenses, and you should be able to describe images produced by diverging lenses. So like what we saw with the converging lenses, it's very difficult for me to draw with the tablet straight lines and perfect angles, so I'll be using an animation to show what I would be drawing on my paper and what you should be drawing on your paper to end up with the proper diagrams. So for our first rule is that if we have an incident light ray traveling parallel to the principal axis, it's going to start at the top of the balloon there, travel parallel to the principal axis, it's going to refract as if it had come from the focus. So this is what that would look like. As if that line had come from the focus, and we can draw a dotted line on the side of the lens to show that it didn't actually come from the focus, but that light ray looks as if it came from the focus, and that's the angle that it will refract from. Our second rule is that an incident light ray that travels through the optical center will continue on in the same direction. And again, we need to draw two arrowheads on that line, one to show the incident ray and one to show the refracted ray traveling in the same line. Now, like all of our other situations, we look at where the light rays cross, and where they cross is where the image will be located. Since we have our light rays starting at the top of the balloon, where they cross will be the top of the balloon of the image, so we can draw our picture like that. Now in the object, the string of the balloon goes straight down to the principal axis, so similarly in our image, the string will go straight down to the principal axis. Now if we're going to describe this image, we would say that it's smaller, that it's upright because they're both facing in the same direction, that it's between F and the lens, and that it is a virtual image because it's on the same side of the lens as the original object. So here are the rules written down. I'm not going to read through these because we've seen them on the animation on the previous page, but if you'd like them in the notes, please just pause the video.
Good day everyone, I'm Angeline Claire Quinto, and here's are the summarization of ray diagram in converging and diverging lens. Array diagrams illustrate the path of light rays as they interact with lenses. In converging lens or convex, parallel rays converge at a focal point on the opposite side of the lens. The central ray passes through the lens undeviated, while others converge or diverge after refraction. Image formation depends on the object distance. Beyond the focal point, real inverted images form, while within virtual upright images appear. Conversely, in a diverging lens or concave, parallel rays diverge as it's emanating from a virtual focal point. The diverging rays extend backward, forming virtual upright images. Understanding these ray diagrams aids in predicting image characteristics and the behavior of light passing through converging and diverging lenses, crucial in optics and lens design.